Hi, my name is Michael.Peroutek, and this is a presentation on my term paper titled Survey of Modern Nature-Inspired Metaheuristic Engineering Optimization Algorithms for Dr. Jiao's 6101 Engineering Design course. Underlying nearly all design engineering decision-making processes is a need to optimize a product's approach to a given design problem. In practice, this optimization, defined as either minimization or maximization, is conducted on an objective function that describes some aspect or aspects of the product deemed important. In the simplest case, this objective function can describe a single engineering parameter, such as a dimension, yield strength, or price. More commonly used in real-world problems are objective functions featuring some combination of many engineering parameters, which must be optimized simultaneously according to some equation or system of equations. These multivariable objective functions can range from basic expressions, such as strength divided by weight, to complex systems of ordinary or partial differential equations. Of course, constraints must be implemented on all variables within the optimization problem to ensure a feasible, realistic engineering solution is identified. A general construction of said optimization problem is presented in these four equations. In the first equation shown, V represents a vector of n variables, each represented here as x sub I. We would like to optimize some objective function or functions g of that variable vector. And there exist constraints on each variable x sub I and constraints on the feasible values of the objective function g. To illuminate the difficulties faced by modern optimization algorithms, we will begin by discussing historical optimization methods. An obvious starting point is the gradient descent optimization algorithm, a mathematical construction of which is shown in the first equation. Gradient descent is simply a quote-unquote hill climbing algorithm which follows the steepest gradient of the objective function and is categorized as first order due to its dependence on the objective function's first order derivative. One can note that the extrema discovered by this algorithm is highly dependent on the initial location of the variable vector, as seen in the image on the right. The two black lines, each starting quite close to each other, converge to different local extrema which may or may not be the global extrema of this function. For this reason, gradient descent is described as being able to exploit extrema, but unable to explore the function domain. Exploit and explore here being keywords used throughout this presentation. To address this lack in exploration, one can imagine a hypothetical optimization algorithm titled the random search, which simply randomly chooses a new variable vector each iteration. This algorithm will do well in exploring the function domain, but has no ability to exploit extrema. From these examples, it is clear that modern algorithms will need some combination of exploration and exploitation processes to consistently discover global extrema. As said before, an algorithm with an efficacious exploitation process should succeed in identifying local extrema, but may or may not succeed in identifying superior global extrema. Therefore, to test an algorithm's exploitation subprocess, it is run on several unimodal benchmark objective functions, shown here on the left. Unimodality ensures that the local extrema identified will also necessarily be the global extrema by definition. On the other hand, to test an algorithm's exploration subprocess, it is run on several highly multimodal benchmark objective functions, shown here on the right. A trend in modern optimization research is the leveraging of metaheuristics in the conception of new algorithms. The term metaheuristic was coined by Dr. Fred Glover as a, quote, master strategy that guides and modifies other heuristics to produce solutions beyond those that are normally generated in a quest for local optimality, end quote. Here, a heuristic algorithm is one that leverages stochastic, i.e. random processes to search for extrema via a controlled form of trial and error. A metaheuristic algorithm is then one that controls a collection of heuristic agents to systematically search a function space. Due to the stochastic nature of these algorithms, they excel in exploring the function domain and exploiting local minima simultaneously. For this reason, metaheuristic algorithms are commonly developed to identify satisfactory global extrema in the optimization of complicated engineering objective functions. Within this category of metaheuristic algorithms, an astute observer would note a surprising emphasis on algorithms with a natural or biological inspiration. Nature, with regards to species behavior, survival, and evolution, is the longest-running observable experiment on optimization. Therefore, it's logical to attempt to mirror its processes in algorithm development. Specifically, modern nature-inspired algorithms fall into four categories: physics-based, which are inspired by physical phenomena; evolution-based, which invoke a Darwinian approach, typically involving some form of reproduction and mutation; swarm-based, which seek to imitate the actions of populations of animals, and finally human-based methods, which seek to imitate human behavior. Here you can see a breakdown of some algorithms within each of these four categories. Note that many more algorithms exist in each category, but only a few are shown here. The algorithms shown in bold will be discussed in detail in this presentation. In the physics-based category, we have central force optimization, simulated annealing, and the gravitational search algorithm. In the evolution-based category, we have the genetic algorithm, evolution strategies, and differential evolution. In the swarm-based category, we have particle swarm optimization, the whale optimization algorithm, and ant colony optimization. And in the human-based category, we have harmony search, teaching learning-based optimization, and human behavior-based optimization. The first algorithm we will discuss is central force optimization, which leverages the concept of gravitational kinematics. This algorithm models quote-unquote probes under the influence of accelerations due to gravitational fields, and extrema are identified by the gathering of probes at a high mass location. In this algorithm, the metaphorical mass is related to the objective function value, often called fitness, at that location. The first equation, shown, calculates the gravitational acceleration on probe P at time step j-1 due to the mass at each other probe. From left to right, the first blue box is the gravitational constant. Next is a unit step function, which ensures only positive masses and thus attractive forces are considered. Next is a chosen mass function, which here is the difference in fitness between the two probe locations. Next is the direction vector between the two probes, and finally is the magnitude of distance between the two probes. This acceleration of probe P is then leveraged in a simple kinematic equation to find the new location of probe P after a discrete time step delta t. Next, the simulated annealing method leverages the behavior of slowly cooled metals. Imitation of this behavior is achieved via the iterative random selection of nodes within the acceptable domain of the objective function. A node's fitness value is then compared to the best node thus far. If the new node is more fit, it replaces the previous best node. If the new node is less fit, it may or may not replace the previous best node. The probability of accepting a quote-unquote regressive node in this manner, i.e. replacing the previous best node with a worse node, is determined according to a Boltzmann-Gibbs probability distribution, which depends on a gradually decreasing temperature parameter. This probability distribution is shown in the equation here. Accepting regressive nodes is this algorithm's method of exploration. As can be seen in the equation, we are more likely to accept a regressive node if either delta G is small, meaning the new node isn't much worse than the previous best node, or if Tk is large, meaning the algorithm is still early in its runtime. Since Tk decreases gradually over time, it becomes less and less likely that the regressive nodes will be accepted, therefore de-emphasizing the exploration process and bolstering the exploitation process over time. Now, entering into the evolution-based category, we have the well-known genetic algorithm. This algorithm leverages a Darwinian perspective on species evolution to approach extrema. The general flow to this process is as follows. First, we have the initialization of a population of individuals. Each individual contains one chromosome, which contains the data from a variable vector v sub I. Each entry within this chromosome is known as a gene. Chromosomes are often encoded in binary to make future steps easier. An example of some binary chromosomes is shown on the right. The processes in this diagram will be explained in the upcoming steps. Next, from this population, a mating pool of sufficiently fit individuals is selected. Most commonly, the 2K most fit individuals are selected for the mating pool, but stochastic variations on the selection process exist in the literature. From this mating pool, individuals are split into mating pairs at random. Each mating pair, consisting of two parents, will now be used to produce two new unique individuals known as offspring. To pass on portions of the parent's chromosomes to offspring, a process known as crossover takes place. The simplest crossover procedure involves first randomly choosing an integer index s between 1 and n, from within a chromosome of length n. Next, the first s genes from parent 1 are combined with the last n minus s genes from parent 2 to form the chromosome of offspring 1. Similarly, the first s genes from parent 2 are combined with the last n minus s genes from parent 1 to form the chromosome of offspring 2. This process, alongside the upcoming mutation process, are shown in the diagram on the right. Finally is mutation. Up to this point, we have created two offspring per mating pair. However, these new offspring fail to contain any new data as they are simply reconstructions of their parents. Thus, a mutation process takes place on each chromosome to introduce new, randomized data to our potential solutions. In the case of chromosomes encoded as binary strings, mutation simply consists of randomly choosing genes and flipping their value. Typically, a singular gene is chosen for this process. Now entering into the swarm-based category, we will begin by discussing the flagship particle swarm optimization algorithm. This algorithm simulates the flocking behavior of birds towards points of interest. Each heuristic agent, or bird, moves in the function space according to one elegant equation. This equation leverages only two data points. The first, pbest, or v star, is the most fit variable vector that agent I has personally visited. And the second, gbest, or vg star, is the most fit variable vector that any agent has visited. In this equation, rand is a random vector with elements distributed uniformly between 0 and 1. The coefficient of 2 ensures that there is an equal probability of the agent undershooting and overshooting its target. By choosing a discrete time step delta t, the velocity of agent I at time step j, as determined by the shown equation, can be simply leveraged to determine the position of agent I at time step j plus 1. The whale optimization algorithm seeks to replicate the unique hunting behavior of humpback whales. This behavior, as might be expected, involves two important processes, one devoted to the exploration for prey and one devoted to exploiting that prey. The exploration behavior is referred to as search for prey, and the exploitation behavior is referred to as the bubble net attacking method, named after the unique humpback hunting behavior shown in the image. Note the matching color scheme between the right diagram and the equation blocks. Orange is exploration, blue is exploitation, and green is the shrinking encircling mechanism subprocess. The equations for the shrinking encircling mechanism used in both exploration and exploitation are shown on the left. When executing these equations, there's a 50-50 probability of encircling the current global best location or a random other agent. Encircling the current global best location indicates the exploitation variation of this subprocess, while encircling a random agent indicates the exploration variation of this subprocess. The image shown on the left depicts this process graphically, where the top right pink point represents the current agent location, the middle pink point represents either the current global best fit location or a random agent, and the lattice represents the outer bounds for the randomized placement of the new node. On the right are the equations for the spiral updating position mechanism, used only in exploitation. The equations here replicate the helical pattern shown in the figure to approach the current global best fit location. On each iteration of this algorithm, one of these mechanisms is executed at random for each agent. Entering into the human-based category, the harmony search algorithm imitates the harmony-seeking behavior of a skilled musician. In this process, a new variable vector is generated by performing calculations on a random variable vector from the population. Each element in the new variable vector is devised from the associated element in the random variable vector according to one of three processes chosen at random. These three processes are 1. Harmony memory, where the element from the random vector is used directly in the new vector. 2. Pitch adjustment, where the element from the random vector is modified slightly then used in the new vector. And 3. Randomization, where the element from the random vector is ignored and the element in the new vector is chosen randomly. Upon generation of this new variable vector, its fitness is compared against the fitness values of the population. If it is more fit than the current least fit vector in the population, it replaces that least fit vector. This algorithm is particularly adept at solving discrete problems, such as those found in the combinatorics of product planning. Next is the teaching-learning-based optimization algorithm. This process involves two phases, each executed concurrently per iteration. The first phase is known as the teacher phase, where the student vectors learn from a chosen teacher vector. And the second phase is known as the learner phase, where student vectors learn via interaction with other student vectors. Within the teacher phase, the teacher vector, chosen as the most fit vector in the population, seeks to raise the mean fitness of the student vectors. This is achieved by altering student vectors according to some value representing the difference between the teacher and the student average. Within the learner phase, student vectors break into random pairs, and the more fit vector within the pair seeks to improve the fitness of the less fit vector. In this process, the more fit vector remains unchanged, while the less fit vector's values are modified to be closer to those of the more fit vector. In both of these phases, changes to student vectors are only accepted if they improve the fitness of that student and are otherwise rejected. To assess the relative performance of these algorithms, a case study is used. The Weld Beam Design Problem is a common case study in the benchmarking of engineering optimization strategies. This problem involves finding the optimal dimensions x, 1, 2, 3, and 4 of a welded beam to minimize cost while meeting constraints on the shear stress, bending stress, buckling load, and end deflection. The discussed metaheuristic algorithms are applied to this problem with the number of agents set as n equals 100 and a stopping criteria of 2000 max iterations. Due to their stochastic nature, each algorithm is run multiple times and their performance and runtime recorded for each run. The data from this analysis is shown in the table on the left, and the average relative performance and runtime are shown on the graph on the right. One can note from this data that the teaching learning-based optimization algorithm consistently found the exact optima in this problem, but had a very high relative runtime. On the other hand, simulated annealing showed an average accuracy in this group of algorithms, but had a very small relative runtime. Also of note is Harmony Search's poor performance on this problem. As stated before, Harmony Search is particularly powerful at solving discrete combinatorics optimization problems, and thus may not be recommended for continuous optimization, as is the case with this Weld design problem.